Hello and welcome everyone to TCP and U, using Wireshark for practical TCP packet analysis. For those who don't know me, my name is Chris Gabrielson. I'm one of our technical leaders within the enterprise switching space of Cisco TAC, and this training is all about how to demystify this particular protocol and make it a little bit easier to troubleshoot. This video is part one of a four-part series designed to accomplish just that. But more specifically, I want to talk about why I made this particular training. I've been in TAC for many years now, over a decade at this point, and I found a lot of engineers tend to see the term slowness as a pretty evil problem description when mentioned in an SR. I think part of it might be because there's no such thing as a show IP slow on the CLI, or you can't configure service act right globally and then suddenly see a fivefold increase in speed. Instead, when cases mention application or performance slowness, it usually means we're going to have a lot of data to collect and a lot of logic that needs to be applied to that data in order to figure out what exactly is going on. That's where this training comes in. Within the next four sections, we're going to try and demystify a bit of the math and logic that's needed in order to understand why TCP might be behaving a certain way. This means that at the conclusion of this training, you should be able to use Wireshark and some basic math to find anomalies and be able to demonstrate to those customers and explain whether or not their symptom is expected. As I said earlier, this is a four-part series, and so the way we're going to accomplish that is through these sections here. For the remainder of this video, we will be covering the basics, and this is all about what we need to collect for a successful packet analysis. It is key that we have good data going into our analysis because just like with case notes, if it's garbage in, it's garbage out. If you have a bad set of data going in, you're likely going to end up with a bad analysis coming out. And so in this section, we're going to talk about where do we need to collect for good packet captures, what does that data look like, what tools are available to us, and we'll briefly touch on certain things like the TCP three-way handshake. Then in part two, we're going to go into the TCP deep dive. We're going to peel back a lot of the layers on how the TCP protocol operates and how some of the external factors, things like latency and packet loss, may come into play in order to affect the speed. Then, once we have that solid foundation, we've got covering the basics and TCP deep dive done, then we can get into common problem scenarios. And here we're going to be looking at a small number of examples that I've pulled out, which are real-world scenarios where the customer experienced packet loss or some issue which caused their slowness to essentially manifest in the application. And within that, we're going to look at that real-world data, and I'm going to show you what I look at in order to make that sort of analysis. Finally, in part four, we've got a few quick tips and tricks for problem solving. Specifically, how could we prove to the customer the network may or may not be the issue? And the example I like to give here is sometimes application slowness is in fact the application. And here we'll be looking at what sort of tools or options are available to us to prove to the customer whether or not the network is at fault. We got a lot to cover, so let's go ahead and get started right into part one, covering the basics. And within this section, I think the best way to start out when it comes to talking about TCP is to cover the golden rule of application slowness, and that is network or application slowness is relative. Right? This is a very important statement. Application or network slowness is relative. Well, what exactly do I mean by that? I've got some icons down below in order to help demonstrate my point. On the far left, I have a snail, then a turtle, then a human, followed by a supercar, and then a jet airplane. If we think about each one of the things in these different categories, they all have a different definition of what could be considered fast versus slow. For example, if I were to take the fastest human on Earth, they would be considered fast compared to obviously other humans, but they would be highly unlikely to beat even an average vehicle in a race. If we now take the fastest vehicle on Earth, the fastest supercar, even that can't beat an average jet airplane, which travels at hundreds of miles per hour fairly commonly. So, because we have this relative perception of speed, right? Again, something like 30 miles an hour. For a vehicle, that is pretty slow, but for a human, that is incredibly fast. But the speed itself does not change. The same thing applies to TCP performance. Because of that, it is key that we always, always, always get two packet captures to begin with. One is going to be our working or our fast example. The other is going to be our broken or our slow example. And the reason for this is sometimes certain things like loss or latency might be completely expected in both cases. Because of that, by having a fast versus a slow capture, we could do what I like to call a stare and compare and look at a lot of the different factors which we'll be covering in this training in order to figure out which one is maybe different or which one is drastically changed from one capture to the other. And based on that, we can usually make a successful analysis in terms of what might be wrong. So remember, if you take away nothing from this training, remember both the golden rule that network or application slowness is relative and that you should always get two packet captures to begin with, one working, one fast capture, and one slow or one broken capture. The next question is, well, where do we collect those captures? And sometimes that doesn't always have a straightforward answer. The example I like to bring up to explain that is in reference to something like application performance. Now, if you've ever dealt with custom applications, a lot of times we might end up with something like this, where I have a front end where I have my user here in blue, and they are going to some sort of web page that is the essentially the front portion of this entire back-end system that we see here. And this user, whenever they go to that web page, depending on how busy it might be, they may be load balanced to one of multiple different servers. Whatever server they go to may then make multiple back-end calls to different services. For instance, this server may need to make a TCP connection to a database server down here. It might also need to make a TCP connection to this file storage server, and it might also need to make a third connection to some sort of application-specific server up here. That server may have its own database located elsewhere in the network, and based on whatever request it gets, it may need to reach out to an application database server. Depending on how the application is written on the front end, if the application server, if it's seeing a lot of latency or a lot of delay trying to pull data from this database server here, the back-end servers may choose not to display all the information to the customer until all of these requests complete in their entirety. That means this one slow TCP connection we see up here causes the entire experience for our user on the front end to appear slow. That means whenever we're dealing with something like this, where the customer talks about multiple back-end servers, we may need to work with them in order to identify a single flow or a single TCP socket which is demonstrating the substandard performance. And that's where, for us, we always want to try and focus on point-to-point slowness. That's going to be our ideal scenario. Something where there's a single TCP socket going between a client and a dedicated server, and there's nothing else that has the potential to hold that up. Now, It's important to also highlight we want to make sure we can keep as much of the environment stable or as much of the environment as common to our fast and slow captures. As seen in the example down below, this particular icon, I may be able to isolate a single client where when it connects to one of three different FTP servers, two out of the three servers are fast and one out of the three is considered slow. But the devices in the path, the network devices in the path, do not change, and I'm not doing something where maybe I'm changing routing or changing some sort of parameter or moving my client. I'm keeping as much of the environment as static as possible. That way we can rule out variables a little bit later on. The other thing that we also need to mention is the use of SMB. Typically, this is seen where a customer has some sort of file share system set up, and in order for them to demonstrate the slowness, they go to a network share, which has a bunch of folders and files, and then they just drag a file from one to the other. And based on the transfer speed, they're using that to measure whether or not it is fast versus slow. If you run into a scenario like this, my recommendation is always encourage the customer to try to get the packet captures before the customer logs into the network share. And the reason is we're going to try and capture the three-way handshake whenever possible, and we'll talk about why that's so important in the coming slides. Now, depending on what sort of scenario we have, we now need a tool in order to get the actual packets as they're seen on the wire. And for that, Wireshark will be your number one tool in order to get a copy of that traffic. The number one thing that I want to highlight, and this is a very common mistake that a lot of engineers make, and it is do not use EPC for troubleshooting TCP performance issues. EPC referring to the embedded packet capture feature that is available on a lot of Cisco routers and switches. The reason we don't want to use this for TCP troubleshooting is because a lot of these platforms have a rate limiter that is on by default and cannot be removed that's set to 1,000 packets per second. A lot of times, a genuine TCP transfer is going to go much faster than 1,000 packets per second. As a result, a good portion of the packets will be discarded as part of the EPC capture mechanism. And so when you go to do an analysis on that capture, you have no way of knowing whether or not the loss you're seeing is a result of the capture method or if it's because there was genuine packet loss on the network. So if you have something like, say, ping loss, where you're just sending an ICMP echo request, EPC is a great tool to use. But if you're using it for TCP performance, it is a very bad choice and should always be avoided. The alternative is to use something like a monitor session or a span. The reason is this can replicate packets at line rate and is not subject to any sort of rate limiter, policer, shaper, etc. Monitor sessions will be best. Additionally, the other thing we could do, depending on what sort of access you have for the source and destination, is you could do packet captures on the endpoints themselves, but we might run into some areas we might run into some problems, which I'll talk about in the coming slides. The second bullet I have here, or the second major section, simultaneous captures are best, but not always necessary. If you have the option to get a simultaneous packet capture, go for it. And what I mean by this is I go to the client, I start the packet capture, I go to the server or the destination, I start the packet capture, and then I start the flow of data. I start the TCP socket. The reason is once we stop the packet captures, it will ensure we have both sides of the conversation for the exact same flow, And so that'll make our analysis a lot easier because now if the client sends 1,000,000 packets, I know that there should be 1,000,000 received by the server. Versus if it's two different sessions, it's not always easy to tell whether or not there may have been loss in a certain direction introduced by the network. And then finally, the last section I have here, always make sure you start your captures first, then start your data transfer. And this is very important because we're always looking to collect that three-way handshake. There are certain fields, which we'll talk about a little bit later, which are only discovered or only negotiated at the very beginning of the TCP flow. And if you start your capture once that flow is already going, it's going to make your analysis a lot more difficult. Now, assuming you've got Wireshark available and you're running captures, the other thing I would definitely encourage you to do is to utilize the conversations window within Wireshark. The way that this works, I have an example here for a Windows client where if you go up at the top, there is a statistics option that will create a menu that then gives you the ability to click conversations. Once conversations is clicked, it will make this window here appear and it will start counting every single packet in your capture up to that point. The reason this is significant is because if you give it a couple seconds, and it might take maybe a couple minutes as well if you're dealing with a very large packet capture, it will categorize it by multiple different flow types. For instance, I have a tab here for the Ethernet. I have one for unique source test IPs, one for unique source test IPv6 addresses, and then here the TCP tab is going to highlight all of the unique TCP sockets seen in this packet capture. When you select TCP, you can then click packets here where my mouse is, and that will sort all of the flows from lowest to highest or highest to lowest if you click it twice. Using that, I can now see what is the largest individual TCP flow in this capture. If you right-click it, you get this menu. Simply mousing over Apply as Filter, mousing over Selected, and then clicking the first option here, this A double arrow B, that will now apply a filter which matches not only your source and destination IP, but matches your L4 port numbers as well. This is extremely important. We always want to look at a single socket when doing a TCP analysis. You do not want to use just source and dest IP. The reason is, even if you look at this example capture I have, my source and destination IP address are both 127.0.0.1. Now, obviously in this example, this would not be something on the network, but what we could see is if I used only the source and dest IP, it would merge, in this case, over 500 unique TCP sockets going between those two IP addresses. If one of those 500 had a lot of packet loss and I started analyzing it as part of a larger capture, it could lead to an incorrect analysis. So by using this filter here and looking at a specific socket with a unique source and destination TCP port, I can ensure I'm getting the best possible data and I can analyze only that one flow. Now, one of the other things that you might see, and this is typically seen whenever you're doing something like a TCP dump on a Linux or Unix server or machine. And that's where if I look at this top left diagram, I have my source and destination IP, and in this column here with all the red numbers highlighted, this represents the packet size. And there's two things that really stand out. First off, is that some of these packets are tremendous. This one is over 14,000 bytes long, much larger than anything we would typically see on the network. The other thing that we see is some of the packets are way too small. Here, the acknowledgement packets are only 54 bytes, and we know that the absolute minimum size is 64 bytes. Well, what exactly is going on here? What you're seeing is a result of where the TCP dump is capturing data. A lot of servers have the ability to capture the traffic a little bit further up in the application stack. And so what we're looking at here is the data as it's going down into the NIC of the server. Once the server sends this down, the NIC or network interface further divides it up and actually fragments it into the packets we would typically expect. It'll carve it up into 1500 byte packets. Additionally, the acknowledgments that come from our client are going to be 64 bytes, but the NIC may strip off things like a .1q header, and it might remove additional padding so that as it goes up the stack, we now see the frame without certain Ethernet headers and without extra padding. That's why it shows up as 54 bytes, even though this was a legitimate packet. What does that mean if we see this in the field? Well, if I get a packet capture and I see it's got these much larger sizes from a TCP dump, I will usually ask the customer to move the packet capture to be a span of the interface where this server is connected. And that's what happened in this example. These two packet captures are actually from the same flow. What the server thought it was sending was what we see above. We see these huge 14,000 or 7,000 byte frames, but what was actually put on the wire in the network was this. Here we see the NIC further fragmented it into multiple 1500 byte frames, and this is different from network fragmentation where we may have the DF or MF bit set. These are just individual packets that were put on the wire, and this is what our switches and routers will actually see. So to summarize, if you see these extra large packet sizes or you see packets that are maybe a little bit too small, realize you might be looking at the expected effect of something like a TCP dump, and instead you can move to something like a monitor session in order to get a better view of what the network is actually seeing. Alright, so now that we have a good understanding of what we need to collect and why, let's get a little bit into the TCP protocol itself, because in the previous slides I mentioned multiple times how important it is to capture the three-way handshake. And so for the next few slides, I want to talk about why this is so important. If you're not familiar with the three-way handshake, this is something that needs to occur for every single TCP socket that is out there. It always happens, but you may not always capture it within your Wireshark filters. The way we could look to see if it was captured is using the display filter tcp.flags.syn =1. Now my animation here is set up to loop, but generally speaking you are only going to send a single TCP SYN, and it's initiated by whoever wants to start the particular socket. And within this frame are a number of options and values that are negotiated only once. The first one that we want to highlight is what is known as the sequence number. Whatever device initiates a TCP socket and sends this SYN, it is going to pick a random number as the starting sequence number. When we look in Wireshark, it's going to give us a couple different fields related to this. The first is the raw sequence number, this middle value here where my mouse is. This is what the client actually chose when it started this particular socket. Wireshark, having a bit of intelligence and knowing how TCP operates, it knows that this number represents the start of the conversation, so it automatically considers this a relative sequence number of 0. And this number is going to increase 1 for every byte of data we send. This means that if my client who is initiating this conversation, if this client sends 1,000 bytes of data, the sequence number should increment by 1000 from this starting number here. Knowing what the size of the payload is and a little bit about the TCP protocol itself, Wireshark will tell you what to expect for the next packet when sending data. So here we know that the raw number is this big number ending in 571. We are considering this the start, so the relative sequence number is 0, and using Wireshark's knowledge of TCP, we know that the next packet should have a sequence number of 1. In addition to the sequence number, we also have the MSS, or maximum segment size. Think of this just like the MTU on a switch or router. This represents the maximum individual packet size that we can send. That is not to say how many continuous packets we can send, but instead any one individual packet, what's the largest that it can be. And so here we have the source device telling the destination how large the packets can be sent. So in this instance, our server here will send a packet that is no larger than 1460 payload bytes. This means that when you look at the packet in the network, it's likely going to be around 1418, assuming a .1Q header and all the additional overhead of both L2 and L3 headers. This is also something that gets modified if you ever go through a tunnel. You'll notice if you were to do a Wireshark capture on your PC when it's connected through VPN or connected through a wireless AP, this is a value which many Cisco switches and routers have the ability to modify on the fly in order to trick the endpoints. The MSS is actually lower than they originally thought, and that causes all of the subsequent individual packets to use that smaller value. Now I said here within the MSS, this is the size of an individual packet, but does not control how many sequential packets might be sent from one side to the other. That is where the window size and window scale come into play. What's important here is that the window scale, so we could see the first value here, window size, the second value, window scale. This scale option is only negotiated in the three-way handshake. The way this operates is the window size and window scale are multipliers, which allows TCP to create a number that that one device can send before an acknowledgement is necessary. So let's take a little bit of a step back in time, a little bit of a history lesson in terms of what it is we're looking at here. Many years ago, before this window scale option existed, we had only window size. In this example, we are set to 64,240. That means one device would only be able to send a maximum of about 64,000 bytes from one side to the other before it must be acknowledged. And the individual number of packets might change depending on this MSS value we talked about earlier. So with a 1460 byte MSS, that would usually be a few hundred packets. Given today's scope and scale of the internet and increased latency, sending only 64,000 bytes in one direction really doesn't work in order to get the sort of speeds we expect today. And so many years ago, the IEEE RFC authors introduced the window scale. And this is where we took window size and allowed a multiplier to be added. This made it where now the endpoints could use a much larger window size than the default 64K that was first introduced when TCP first came out. Today, this value can actually go up, I believe, into either hundreds of gigs or maybe even terabits, to the point where now it'll be future proof for many years to come and won't arbitrarily limit packet transfer speeds. And we'll talk about how that works a little bit later on in the presentation, but that was just a brief history lesson on window size and window scale. So once our destination gets this SYN with all of these frames, it now needs to acknowledge them, and because TCP is bidirectional, it needs to choose some values of its own. And so here our client, or our server rather, will acknowledge this initial SYN with an ACK, and it'll send a SYN of its own. This is known as the SYN ACK. And like before, just a single packet will be sent. I just happen to have a loop going so that we're going to see the same frames going back and forth like we see here. The way we could look at it within Wireshark is this display filter, TCP flags SYN double equals 1 and tcp.flags.ack double equals 1, and that will give us only the SYN ACK. A couple things are going to be happening here. If I look at the original SYN, we could see that random number that the client chose now gets adopted as the acknowledgement number of the receiver. The receiver also chooses its own random number. This follows the same rules as before, and the way the destination acknowledges the use of this number is it's also going to increase the ACK number by 1. This means if I were to look at this raw number here, we will see it is increased by exactly 1 from where it was before. That's how the receiver now knows that this device is in sync. Down below, we also have a lot of the same values which are getting negotiated. Things like MSS, window size, and window scale. However, these are going to be different because this is covering data transfer in the other direction. TCP is bidirectional. That means if you connect to a server, you can upload data, but you could also download data using the exact same socket. Before, if I were to look at things like the MSS, it was a value of 1460. Now, my MSS on the other side is also 1460. The window size for the client was 64240. Here, the server has a slightly different window size of 8192. Once our client receives this SYN ACK, it now must acknowledge those settings that were sent by the server. And this one is fairly straightforward. Again, we're only going to send a single ACK. Don't pay too much attention to my animation. And if we were to look at the packet in Wireshark, there's really nothing that uniquely identifies this because a lot of packets are going to have just the ACK flag. But the way we could tell that this is for the three-way handshake is because my sequence and my ACK numbers are both set to 1. This indicates that both the initiator and the receiver agree on the different numbers that they will be using. In this case, we have the raw sequence number for data in one direction, and we have the acknowledgement number, which is the sequence number of the other side going in reverse. Now let's take a little bit of time to better understand how this sequence and acknowledgement number system is going to operate once the three-way handshake is complete. And I like to call this out because this could be a very confusing topic for engineers, and it's very easy to make mistakes if you don't know what exactly it is you're looking for. To start off, we're going to assume the three-way handshake has now completed based on the previous slides. So the sequence and acknowledgement number are both going to be 1. In the previous example, we had an MSS of 1460. I'm going to pretend that it was 1500 just so that it makes our math a little bit easier and makes this flow a bit simpler to follow. Now what's going to happen is my client, now the three-way handshake is complete, it wants to send data to the server. The client is going to start off by sending one packet with some payload, followed by some subsequent packets with their own payload, but you'll notice the sequence number continues to increment. The way I could tell that the server received all 4 blocks of data is through this acknowledgement frame. And there's quite a bit that's going on here, so let's break it down in terms of what we see over on the right. The first packet represents the starting sequence number and then has some payload. This means the next packet that I have zoomed in here represents where we are starting before the payload that is to the right. Because the first packet had 1500 bytes and was starting at sequence number 1, this means the second packet now picks up where the first one left off. What we're telling the receiver here is put this right after the 1500th bit. We then have another 1500 bytes. And so if the destination wanted to acknowledge that, yes, I got up to this starting sequence number, plus I got this payload that came with the data, it needs to acknowledge right where my mouse is now. It needs to acknowledge the end of this entire payload. Well, if our payload is 1500 bytes and we started at 1501, we simply just need to add these two numbers together. And so the server will send an acknowledgement for 3001. And this implies that we got all of the bytes, including the entire payload, up to the 3001st bit, or byte rather. Once the client now gets this, so here we can see we start at 1, we have a 1500 byte payload. Therefore, this packet ends at 1500, so the next one will pick up at 1501. It also has a 1500 byte payload, so the next frame will now start at 3001. It has a 1500 byte payload, so the next one starts at 4501 and has a 1500 byte payload. When I add these two numbers together, that's where we get this acknowledgement of 6001. And I have a very important note here, and this is where a lot of engineers get stuck. If you see a sequence number of whatever the value is, in this case sequence 1, 2, 3, 4, and then you see an acknowledgement for 1, 2, 3, 4, that acknowledgement is not actually for packet 1, 2, 3, 4, it's for the one immediately before it. If I were to continue this animation now, we can see the next packet sent by the client actually has a sequence number of 6001. So the acknowledgement of 6001 comes first. That tells this sender that the destination has acknowledged the last of the payload in the previous packet that I sent. Therefore, the next frame can now start where this acknowledgement left off. That is why the ACK of 6001 now sees a sequence number of 6001 after it, and the cycle continues. We start at 6001 with a 1500 byte payload, and every packet picks up where the previous one left off, and the client now gets an ACK for the last two numbers, which indicates all 4 of these packets were received, because I'm acknowledging, last time I acknowledged was up to the 6000th bit. I then sent another 6000 bytes, and I acknowledged all 6000 here. So I've continuously acknowledged all 12,000 bytes of data with just these 2 packets. And so this is going to be the end of part 1. So let's quickly go through a checklist before we get into the deep dive. few things that we need to make sure we always do, and that is to obtain the exact source and dest IP known to be slow and L4 information. We also want to clarify with the customer whether or not this is an application server with a back end that might need to be investigated separately, or if this is an individual socket like FTP, which we know is not performing as expected. Additionally, whenever troubleshooting slowness, we want to make sure we always get at least two captures. One needs to be the working or fast capture, the other needs to be the slow or broken capture. Additionally, if you're using something like TCP dump on a server and you see packet sizes that look a little bit unexpected, you may want to instead collect a span capture on the device where that server is directly connected in order to get a better view of what the data actually looks like on the network. Number 3 is do not use EPC to collect TCP captures. EPC is a great tool for something like ping loss, or if your capture did not initiate at all, maybe the three-way handshake fails to complete, EPC is a great tool. But if your three-way handshake is working and the transfer itself is just slower than you would expect, EPC is the wrong tool and will introduce false positives into your data. Next point down, always make sure you start your captures first, then start the application and the data transfer, because we want to make sure we collect that three-way handshake, since there are certain fields which are only negotiated there and nowhere else in the capture, one of which being things like the MSS as well as the window scale option. And then finally, simultaneous captures are best, and we always want to work to get a simultaneous capture as opposed to two different captures of two different sockets, simply because it's going to make our analysis a little bit more difficult. And if it's simultaneous, it's very easy to figure out, did all of the packets sent by the client make it to the server, and vice versa. And that concludes part 1. I hope you enjoyed this section, and in part 2 we'll be going into our TCP deep dive.